Hello everyone, my name is Mutiana Mwamba. I'm a research professor from Korea University, Blockchain Research Institute. Today I'm going to introduce about our paper, which is titled AgroChain Plus, a secure, decentralized, and trustworthy agricultural products traceability system using blockchain-based IoT. The global agricultural supply chains have evolved into complex networks which involve multiple stakeholders, ranging from producers and distributors to retailers and regulatory authorities. Ensuring food safety, quality, insurance, authenticity, traceability, and transparency across these multi-party transactional network is remaining a big challenge, primarily due to the differences into data ownership, many technologies which are heterogeneous and varying compliance requirements involved in this domain. Recent incidents of food contamination outbreaks highlighted the lack of trust and transparency within traditional systems, which require effective traceability and accountability mechanisms. These show the critical importance of systems that enable traceability and accountability into agricultural supply chain to restore trust among the participants, especially the consumers. Traditional centralized systems have proven to be inefficient as they are subject to a single point of failure with the fragmented architecture and the vulnerability to frauds, which affects the lack of trust among the participants. Difficulty also in ensuring security, transparency, and efficient traceability, especially in resource-limited environments. Thanks to the blockchain-based IoT traceability system emergence, which offers a potential solution to address data fragmentation, integrity, and accountability, which is useful to strengthen the stakeholder confidence into the supply chain. Many existing solutions presented only proof of concepts without adequately addressing scalability, interoperability, and the cost effectiveness in resource-constrained contexts. To address these limitations of existing cultural supply chain systems, we proposed AgroChain Plus, which is a secure, decentralized, and trustworthy traceability system integrating blockchain with IoT to provide verifiable end-to-end product tracking. It is a lightweight and viable traceability framework with reproducibility and low-cost deployments, which make it suitable for resource-limited agricultural ecosystems. The contribution of this work are fourfold. First, we designed a lightweight blockchain-based IoT traceability system architecture, which is designed for resource-limited agro-food supply chain with privacy-aware data flows and role-based access control, which is integrated to manage the access to the network. It is also incorporating IoT-enabled real-time data capture and smart contract for end-to-end automated verifiable performance evaluation has demonstrated the scalability, low latency, high throughputs with enhanced trust while remaining cost-effective. We also identified the key challenges for large-scale deployments, including the interoperability, stakeholder adoption, and data protection. In this figure, we illustrate the key participants into the AgroChain Plus supply chain network with the interaction, including the producers, the distributors, the transformers, the retailer, and the end consumer, which are interacting into the supply chain by exchanging information. But with the existing centralized architecture, it has proven to lack transparency throughout the supply chain. The proposed AgroChain system architecture integrates IoT sensing device layer with the application layer, which is integrated with the blockchain using JavaScript SDK through the contracts, which are built as a Chaincode running on the Hyperledger blockchain network, where participants that belong to organization are transacting on a channel of communication. On the application layer, the UI interface that's giving the users to interact with the blockchain and read the data collected from sensors. And every product is assigned a QR code for getting access to the details about the history of the products and the transaction. The design of AgroChain Plus prioritizes resource efficiency, security, and transparency, where IoT sensors capture real-time data such as temperature, humidity, and location. Environmental data is sampled every 10 seconds, while aggregated data batch are committed to the blockchain every hour for efficiency. Data flows through MQTT using Node.js API, and it is stored to PostgreSQL transactional DB. We adopted a hybrid model that store raw sensor data into off-chain into Postgres transactional DB, and cryptographic hashes are stored to a blockchain And we adopted Hyperledger Fabric as the permission blockchain for its efficiency in terms of performance and its optimized architecture. Each product's batch is assigned a QR code for a consumer to verify its history. In this slide, provide the operational flowcharts for the main operations, such as the IoT data collection and recording, which is illustrated in the figure 8, where the data is sent from the Raspberry Pi IoT sensor and collected by Mosquito, which is a component that interacts with the server that processes the data and store the data on the database, which return the proof of registration and insert the parameters, collect the timestamp verification, and all the metrics are recorded into the hashed version in the blockchain for proof records which are tamper resistant. On the right side, we have the figure B, which shows the transaction flow of the AgroChain system, where the user submit their request to the server, which communicate with the blockchain through the SDK fabric, and the signed transaction is sent as a proposal to the peer endorser that endorse the transaction considering the endorsement policy, and the endorsed transaction is sent to the other nodes, which put the transaction into the block and broadcast the block to the peer committers, who validates the block containing the endorsed transactions and append that to the blockchain. Upon successful execution of the transaction, the notification is sent to the user. We have enhanced the data integrity by establishing a trustworthy and tamper-resistant transaction recording framework. We use smart contract for automatically enforce the predefined business rule and reduce the need of intermediaries and manual operations. The smart contract-based role-based access control is implemented to ensure that only authorized participants can access private data and perform specific action within the network. Digital signatures are used to provide ownership control, ensuring data authenticity and integrity, and also preventing unauthorized data modification and tamper with. Abnormal events such as temperature spikes are instantly detected and immediately recorded on the blockchain as a proof. The prototype implementation and experimental setup is described in the table below, where we use a computer HP Elite book for our simulation experimental tests with CPU 1.8 gigahertz with 4 core. The memory was 1600 gigabytes, and the system was Ubuntu as operating system. We use Node.js and Mosquito for as framework for implementing the decentralized application, and the Docker engine was used for running Docker, which was defined by Docker Compose. And we use OpenSSL for secure communication. The Hyperledger Fabric sample version 2.5.13 was used for the test environment, and the Hyperledger Fabric Network Peer version 2.2.20 was used. And we also use JavaScript to write the Chaincode smart contract, and the consensus protocol that was used was Raft protocol. The experimental result demonstrated the robustness and excellent performance of the proposed AgroChain Plus system, as you can notice in these figures comparing the system performance for writes, transaction, and the variable workloads. Figure A shows the measurement of transaction latency compared to the transaction success and failure rates and the variable transaction submission rates. As you can notice, the transaction latency increase linearly as the transaction submission rate per second increase. It reached maximum of 20,000 milliseconds for 4,000 transactions submit per second. But it's reached a peak of saturation at a transaction submission rate of 2,500, where the transaction success rates start dropping down and the transaction failure rates start increasing. This shows that the transaction submission rate is affecting the transaction latency. As the transaction workload increase, the transaction latency also will be affected. On the right side, we have the throughputs and transaction success and failure rates measurements, where we can see that it has achieved a fluctuating transaction throughput that has reached a peak of 121 transactions per second. Transaction failure rates start increasing at a transaction submission rate of 2,500 transactions, while the transaction success rates start dropping at the same point. This also confirms that the transaction submission rates is also affecting enormously the transaction throughputs. For read transaction, the figure A shows that the transaction latency for read operation increased linearly with the increase of the transaction submission rates, and it reached a peak of 2000 milliseconds for 4,000 transactions submitted concurrently. And the transaction failure rates start increasing from transaction submission rates of 2000. At the same point, the transaction success rate starting dropping down. This also confirms the relationship and the impact of the transaction submission rate on the transaction latency. On the figure B, we can see that the transaction throughput increased slightly while it reached a peak of 227 transactions per second. It's with a small increase, but the transaction success rate started dropping at a transaction submission rate of 2000, while the transaction failure rates increased linearly. This also confirms the impact the transaction submission rates has on the transaction throughput. The results prove the feasibility of integrating IoT and blockchain to enhance data integrity, transparency, and traceability into the agricultural supply chain. Practical implication, as you can notice, the stakeholders can gain access in real time to tamper-proof transaction records and get in real time information on the environmental and the product condition, which increase the trust and confidence between all the participants within the supply chain network. For limitation and challenges, the current prototype was tested and validated on a small scale prototype rather than a large-scale deployment, which needs further optimization. The scalability remained a key challenge at very high transaction submission rates. Digital literacy and stakeholders adoption also remain barriers, especially in developing countries and rural areas. Compliance with diverse and heterogeneous global regulation also remain a big challenge. For the next step, as future work, we plan to extend to other domains such as fisheries and pharmaceutical supply chain domain. We plan to integrate AI for predictive analytics and anomaly detection, improve the interoperability with existing certification for the security and the legacy logistics systems. In summary, in this paper, we present AgroChain Plus, which is a blockchain IoT interoperability framework for enhancing security, transparency, and trust into agro supply chain. It's a lightweight hybrid architecture for on-off-chain data management, where IoT data is stored off-chain into a Postgres transactional DB, and the hashes are stored into a permission blockchain. Smart contracts are used for automating all the operation, and the role-based access control is integrated to control the access and the operation into the network for accountability. Temporal constraints also are used for integrity and scalability purpose. The developed prototype was deployed on Hyperledger Fabric using Raspberry Pi sensors. We proved the feasibility of the proposed solution on low-cost hardware. The performance showed strong potential for real-world adoption, where the transaction latency could reach an average of 15.6 milliseconds for write operation and 2.11 milliseconds for read operation. And the throughput was for write operation 121 transactions per second and 227 TPS for read operation with high reliability. In the future, we are planning to conduct pilot tests on diverse agricultural and other supply chain sectors. Thank you for listening. I'm open for any question and comments that will help us improve our solution.